do this 2-5 thing. Good news is, like, the first pass through everything I told you was right. Like, I was doing it the right way. It was fine. I was second guessing myself. We'll go back through this in a minute, but the reason it felt weird to me was for whatever reason, I was missing the 2-5 notes, and we didn't do those yet. That's why it felt weird, because I was supposed to come after this thing. So that's why I felt all turned around. I'm like, what is going on? Anyways, so that's what's going on. So we're going to do 2-5 today. And yeah, sound good? So we might circle back to that 2-5 bonus after we finish 2-5 and like finish that up, because there's still a little bit more I want to talk about there, and then just review it so that you feel like your teacher confidently knows what he's doing. I know. It was embarrassing, guys. I was embarrassed for myself. All right. In section 2.5, we are going to be talking about continuity. So I think intuitively we know what continuity means, right? If you have a continuous function, you can draw the graph of that function without having to pick up your pencil. Basically, it means there's no discontinuities there. The three types of discontinuity we've talked about would be like an infinite discontinuity, like a vertical asymptote, a removable discontinuity, like we have in some rational functions where there's just a hole in the graph, and then a jump discontinuity where like it's a piecewise function that doesn't connect, right? So what we're going to want, though, is a mathematical definition for continuity, so that's something that we could prove without having to draw, result to something as squishy as I can draw the graph without picking up my pencil, right? So we say that a function is continuous at a point at a specific value a if the limit as x approaches a of f of x is equal to f of x. So remember that when we say a limit exists, that means that its left-hand limit and its right-hand limit agree. So you could also think about this same definition as the left-hand limit equals the right-hand limit, which equals f of a, right? That all three of those things are equal. So again, the reverse is true. So if I have continuity, I can say the following three things that are listed here, that we know f is defined at a, f of a exists, so there is a value there. The limit exists, and that the limit is equal to the y-coordinate at a, is equal to f of a, right? So let's take a look here at an example. So figure 2, that's the picture you're looking at, shows the graph of a function f. At what numbers is f discontinuous and why? So hopefully it's really easy to see where the discontinuities lie. Where are the discontinuities at? 1. Where else? 3, great. And where else? 5. Okay. What part of our definition of continuity does x equals 1 fail? Right, we have a definition for continuity we just talked about. Right, what part of that definition is it failing? Well, I would say it's because we're not defined at x equals 1, right? Everybody's okay there? There's no value when x is equal to 1. That doesn't exist. That's the problem. How about for 3? What's the problem? And when x equals 3, what is our problem? Okay, good. Okay. And what's the problem at 5? At x equals 5, what's our problem there? The third one, that the limit doesn't equal the y coordinate, right? Because the limit looks like it's 1 and f of 5 looks like it's 3 or something. Right? There's no scales here on the y coordinates or the y-axis, so we're just kind of guessing, but clearly they're not equal. Everybody's cool? We understand how to use the definition here a little bit? Okay. So next example, we're going to look for places where the functions are discontinuous. So here you're given an equation rather than a graph. Let's look at part A. How would we go about looking for where that function is discontinuous at? Find the hole? Or are we guaranteed to have a hole here? Could also be an asymptote, right? Does it matter, though, which one it would be? Either one of them are discontinuities, right? How do we find that? What's up? Well, without using a calculator. Great, exactly. We're just worried about what makes the bottom 0, right? So x equals 2. Everybody's good? Even if it reduces out, that creates a hole. If it doesn't reduce out, that makes an asymptote. Either way, that's a discontinuity, right? And those are the only places where a rational function can be discontinuous, is where the denominator is 0. Everybody's cool? Okay. How about for part B? If I look at the first piece of my piecewise function, where can that be discontinuous at? Where the denominator is 0, right? So x equals 0. If I look at this, where can that be discontinuous at? Nowhere, right? That's a continuous function. It's over its entire domain. So the only place I need to check is where x equals 0 and the boundary between the two pieces, right? Now, that happens to be the same value, so I really only have to check x equals 0. Do I know that x equals 0 is going to be a discontinuity here until I check it? I do not, right? So I know that the limit as x approaches 0 from the left of f of x is equal to 1 over x squared. And the limit as x approaches 0 from the right of f of x, is equal to the limit as x approaches 0 of 1 over x squared. Everybody's good with how I can say that? The left-hand limit is x not equaling 0, and so is the right-hand limit, so it's the same one, right? So those clearly have to equal each other, right? What is that going to, though? What number is it going to? Do you remember what the graph of 1 over x squared looks like? How about just 1 over x then? One over x would look like this, right? 1 over x squared It's just going to look like a steeper version, but you're going to be stuck on the positive side of the x-axis because it's x squared. Can't make it negative. And since it's squared, it'll just be like a little steeper or whatever. You know, if it's a small number, it's just going to be smaller when we square it. If it's a big number, it'll just be bigger when we square it. So, everybody's cool? So what is that heading towards then when we go to 0? Infinity, right? Which is not f of 0. So we know that x equals 0 is a discontinuity. Everybody cool? Okie majokies. How about C? What's the only value we have to check? Still 2, right? Because it's both what makes the rational function, gives you a 0 denominator, and it's where the boundary is. So it's 2 for 1. So really, the same kind of thing applies because it's a not equal to here. We have that, right? So if I try doing a direct substitution, I'm going to get 4 minus 2 minus 2 over 2 minus 2, so 0 over 0. That tells me nothing, right? So I'm going to have to do some kind of algebraic trick to clear that indeterminate form hurdle. What can I do with this particular limit? Yeah, I heard somebody say factor. How does that numerator factor? Times x plus 1, right? And now we get a place where we can direct substitute. And I notice that that is not equal to f of 2, which is 1. So yes, x equals 2 is also a discontinuity. Is everybody cool with how I'm using my definition of continuity to check these things? It's not just a yes or no question. We expect you to like verify or show why it's a discontinuity. So doing that is not drawing the graph. It's like doing a limit, right? Everybody's cool? So the discontinuity is at x equals 2, right? That's the value of x that we're checking. And the reason we know it is a discontinuity is because the limit as x approaches 2 is not equal to f of 2. Because the limit was 3 and f of 2 is 1, right? So that's our reason. So again, as I mentioned before, we have like different types of discontinuities. So this one is like a removable, right, where there's just one hole in the graph, just a missing piece, one missing point. This is like an infinite discontinuity or a vertical asymptote. You could use those words interchangeably. We have, I'd still call this a jump discontinuity, even though it's 1 point. The only way you're going to write that is with a piecewise function. And then similarly, I'd call these jump discontinuities. Again, the only way you're going to really write that is with a piecewise function or a new function that you've defined from a piecewise or something. Like that's really a step function or like a least integer function, like a round down function, like round down to the previous or to the previous integer. So any decimal, like bigger than 0 but less than 1 rounds down to 0. Any decimal between 1 and 2 rounds down to 1. You know, you guys talk about that in pre-calc last year as a type of function? Sometimes you might not. It doesn't matter. It's an example of something that's like, this is a piecewise function, but we're going to define a name for it that's like just, you know, you call it the least integer function. Or you could have like the greatest integer function where you just round up. Same idea. Everybody's okay? Okay. And like the book has some notation for it. I've never seen that double bracket notation. That's what they're doing there, is they're putting like 2 brackets around the x. I don't use that notation. I wouldn't use that notation. The AP doesn't use that notation. You don't have to know that notation. But that's what that notation is. It's just the book's notation for like that least integer function, which is just a type of piecewise. Then instead of writing the giant piecewise thing, we just have a symbol for it. Okay. So in talking about continuity, it becomes necessary to talk about a situation like if we have a square root function, where a square root function looks like this, right? Now, technically, what would be going on at this limit? That limit doesn't exist because there is no left-hand limit to it, right? There's no function going into that last point because it's the start. So, but we'd want that still to count as continuous there, right? Since we drew it with like 1 stroke of the pencil. Everybody agree? That should still seems like that we want to count that as continuous. So we're going to make up a name for something like a point like this. We'll say this is continuous from the right. And in the case of a situation like this where there is no left-hand limit, continuous from the right will be good enough for a continuity for at that point. You know what I'm saying? So we're just building out some vocabulary so we can deal with that. So we have the idea of continuous from the right or continuous from the left, where the limit from the right is equal to f of a, or the limit from the left is equal to f of a. And in a case where you have only one-sided limits, that's good enough for continuity. So that's what we're doing here in definition 3. We say a function f is continuous on an interval if it is continuous at every number in the interval. And then it says if f is defined on only one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the left or continuous from the right. Does that make sense? So it's dealing with this square root function is that, okay, if we have, like it's only defined on one side, if it's continuous from the right, then that's good enough to say that continuous at that point. It's okay? Again, I think that like the verbiage in here is kind of technical. The pictures I'm drawing and hopefully talking through should feel pretty like, okay, I get what we're making an exception for here. That makes sense. Never will I ask you to like rewrite a definition. Never will I ask you to quote a theorem. You just have to be able to understand it and use it, kind of thing. So example 4 here says to do something different. Here it says that we want to show that the function f of x is continuous on the interval from -1 to 1. So how many values of x are on the interval from -1 to 1? It's not really a trick question here. What? Oh, way more than 3. It's infinitely many, right? You have like negative 0.9999, negative 0.99998, negative, you get it, right? Like, we have all the decimals in there. There's infinitely many. Mr. Kulik, how are you going to check continuity for infinitely many points? Well, here's what I'm going to do. I'm going to say A is just some number between -1 and +1. I'm not counting the endpoints of my interval, but just A is something everywhere in between. Everybody's cool with that? So all I'm going to do then is I'm going to check the limit as x approaches A. And using my limit laws, I guess I should put a parenthesis there, I know that I can distribute my limit. So I have the limit as x approaches A of 1 minus the limit as x approaches A of square root of 1 minus x squared. Well, that limit is 1, right? And the limit as x approaches A of the square root, well, that's a continuous function. So I could just do like a direct substitution, and I have that. Everybody's okay? If I do f of A, I get the same thing. So we're good, right? So I've shown their continuity on the open interval from -1 to 1. The other piece that I need, though, is the endpoints, which I will check separately. So far, so good? You guys aren't giving me a lot back, and that's okay, but I need to know that, is this okay or not? So I know if I should explain some more, if I can stop and explain some more, if I can continue on. It's okay so far? Okay. So if I do at x equals 1, or -1, excuse me, that is going to be a left-hand limit only, because I know if x is less than -1, I'm going to end up with a negative under the radical, right? That's all I can do. So that's a right-hand limit only. But that's okay. That'll just do like a direct substitution, and I get 1. And f of -1 also gives me 1. So we're good there. And likewise, since it's a closed interval, I only need to check the endpoints on one side. But again, I can just do my direct substitutions, and those are equal, so I have continuity across the entire closed interval. So if you're looking for continuity on an open interval, where there's infinitely many, you just create some arbitrary variable that's in that interval, and you do it kind of non-specifically, right? Where you just use like an A or a B or whatever letter you feel like. Probably not another X, because you're already using X in the f of X. Y, Z, taco, Yeti, whatever you want to use as your variable. Usually I get a chuckle out of those. The idea of putting a Yeti, drawing a little... No? Okay. It's 4th hour. You're fine. But that's the trick, if you have to check an entire interval to do something like that. Okay. Now, in general, we would prefer not to have to check every function for continuity. So we're going to create some rules or some theorems for continuity that allow us to kind of speed through that a little bit. So if f and g are continuous functions at A, and c is just a constant, that if I take two functions that are continuous at A and add them together, the result still continuous at A. If I take two functions continuous at A and subtract them, the result is still continuous at A. If I multiply them, still continuous at A. If I divide them, as long as the denominator is non-zero at A, the result is still continuous at A. If I multiply by a constant, the result is still continuous at A. Which should come as no shock, right? If I think about two graphs that I can draw with my pencil, if I add them together, it's just like adding the y coordinates and plotting, like the result is still going to be all connected. Everybody's okay with that idea? Should you be like, this is what I would hope it would be, right? This is how you'd hope it would work. The next theorem says any polynomial is continuous everywhere. We knew that already, I hope. But there's a theorem. So if I have polynomial plus polynomial, I know that's continuous because each polynomial is continuous, and continuous function plus continuous function is continuous. Everybody's okay? Any rational function is continuous over its domain. So again, it's essentially theorem 5, because a rational function is just a polynomial over a polynomial. So it's continuous everywhere except for where the denominator is 0. Okay. So let's say we have this question asks us to find the limit as x approaches -2 of yada, 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 yada. What I notice is that this is a rational function. It's continuous everywhere over its domain. The only place where it's not continuous at is going to be where the denominator is equal to 0, so like 5/3. Is that where the limit is going to, 5/3? No, the limit's going to -2. So what that tells me is I can just do a direct substitution and be done. So we just plug it in and be done. Since we have a function that's continuous at A, that's enough to just do my direct substitution. Oops. It's -2, not -5 there, genius. And then you get whatever you get, right? Doesn't matter. Let you do the computation, but is everybody okay with why I was able to do direct substitution there? Even though this is not a continuous function, it's continuous over its domain, and we're not looking at a discontinuity, so we're good to do a direct substitution. Okay? Yes, Paul. Of course, yeah. Now here's a nice one. Okay, well, what functions are continuous over their domains? Essentially every kind of function you've studied so far. Polynomials, rationals, roots, trigs, inverse trigs, exponentials, logarithmic, all continuous over their domains. So if I take, like, if I'm looking at the limit of, like sine plus log, limit of sine of x plus log of x, continuous plus continuous is continuous, so I can do a direct substitution. Even though I don't know what the domain is, doesn't matter. Those are continuous, over their domains. As long as it's that what x is going to isn't at a discontinuity for either one of them, we're good to go. Just direct substitute. Is everybody seeing the power that we're creating here? It just is basically allowing us to direct substitute into anything as long as you're not direct substituting into a discontinuity, right? Okay. So if I look at example 6, it asks, where is the function continuous? So what I'm going to do is I'm just going to look at each piece or each representative function. So where is natural log of x continuous? What's the domain for a natural log of x? Ooh. Can't be negative, and it also can't be 0. Yeah, very good. What's the domain for tan inverse? Okay, who remembers what the graph of one period of tangent looks like? It's kind of like this, right? So the inverse, we're just going to rotate that about the line y equals x. So you're going to get something that looks like that, right? Everybody's good? What's the domain on the green one? Just all real numbers. Yeah, it's no trick there. And then I know that the polynomial, what's the domain on a polynomial? All real numbers also, very good. And then we also have to worry about the fact that this is a rational function, right? Where is that denominator 0? 1 and negative 1, right? Oops. Everybody's good there? So, yeah. Huh? I looked at where the denominator was 0. So x squared minus 1 factors to x plus 1, x minus 1. So the two zeros there are 1 and negative 1. Okay. So what I want to do now is I want to look at the intersection of these sets. So I know that this can't be part of my domain, right? Because any negative is going to be a problem for the log. You guys see that? So the smallest value I can have is that first value after 0. But then I can't have 1, right? Because that's a problem for the rational function. But then anything bigger than 1 is fine because that's in every other value. So that would be like my domain. So 0 to 1, and then 1 to infinity. Any x from that I can plug into that function and get something to come out. Notice that the tan x didn't really matter because its domain is all real numbers. And the x squared minus 1 didn't really matter because its domain was all real numbers. What mattered really was the log and the rational function because those are the only two with the restricted domains. Of course. Do we feel okay on that?
So the answer is the green.
The answer is the green, yep. I was just kind of writing down the work because I have to check all the domains before I can give the domain for the big one. But that's how we do it. We look at each chunk, and then we just take the intersection of those sets. So you have to have the stuff that's in all of them. All right. If I look at the next one, I see I have a rational function, right? So the numerator is a trig that's continuous over its whole domain. What's the domain for sine x? That's the range, is negative 1 to 1. The domain is all real numbers, right? You can do sine of any angle. That's the first thing that you do for trig is like build out our definition from being stuck inside a right triangle to being something you can do on any real number. Likewise, for cosine, the domain is all real numbers. So we have Then we have to worry about the rational function piece. So 2 plus cosine x, can that equal 0? No. What's the smallest output cosine can have? -1, right? I can't ever get to enough to cancel out 2 to make it 0, right? The smallest cosine x can ever get is -1. So my domain here is all real numbers. Everybody agree? It's continuous everywhere. Neat. What does that tell me for the limit? I can just do a direct substitution. Is that okay? All right. Remember your unit circle. What's sine of pi? Cosine of pi? -1. Okay. Real time talk here, folks. On the AP exam, your equation sheet is a blank sheet of paper. If you don't walk into the exam with it in your head, they're not going to give it to you. One of the expectations would be you can do unit circle trig without a calculator from your head. So it's usually not anything tough. They probably won't have like a 30-degree angle in here, but you're definitely going to have quadrantal, like 0, pi over 2, pi, 3 pi over 2, 2 pi. Like those, you got to have dead cold for sure. Okay? Just trying to be honest with you. At one point, I know you memorized this last year because Mr. Myers told me he gave you guys like 100 unit circle quizzes until you passed them, right? So if you need to refresh on that, make sure that you've kind of refreshed on that. I wouldn't put him past doing like a 30-degree or 45-degree or 60-degree equivalent in there. But you definitely for sure need the quadrantals, right? Where it lies, where your unit circle is on one of the axes. Mm-hmm. Okay. Next up. This is an incredibly useful theorem. It allows you to do limits of compositions using direct substitution. We do have to be careful about this, though. So in order to make this, or to do this, to push the limit inside the function, you have to have that f has to be continuous at the limit of its input, right? So if I have the limit of the inside as 3, and f is not continuous at 3, I cannot use this. This is what I was trying to show you on that other slide. We'll go back to that other page and go through and show you the case. The 2 examples at the bottom are ones where we have to be really careful. We didn't get to them yet. Because I was like, why does this feel like I'm missing something? And this is why. It's because I didn't do this part yet. Okay, so let's look at an example here. So this is the limit as x approaches 1 of arc sine 1 minus root x over 1 plus root x. What is arc sine again? Just sine inverse, right? Yeah, inverse sine, sine inverse, whatever you want to say. Good. So what is the domain for sine inverse? Do you remember? I think it's negative pi over 2 to positive pi over 2. Okay, hold on. So again, think about what the graph of sine looks like. One period is this, right? If we flip that you have something like this, right? You reflect it across the line, y equals 1, you have that graph. What's the problem with the green one? It's not a function. So what we do is we restrict the domain. We just go from negative pi over 2 to positive pi over 2. So when we do that, the inverse looks like this. Is that okay? And I think those are bracketed. That's your domain for sine inverse. Does this ring a bell? I'm sure you talked about it last year. It's okay if it's not fresh. So let's look at the limit as x approaches 1 of this and see if that is indeed inside of negative pi over 2 to positive pi over 2. If it is, we just plug it in and we're done. We plug it into f and we're done. If it's not, then we got a little bit of work to do still. If I try to do a direct substitution here on the limit I've written in green, what do I get? It's 0 over 0. That's bad news, right? So I'm going to have to do something algebraic to clear that indeterminate hump. What do you want to do here? You could multiply by the conjugate. That'll work. What I would do here, though, I want to be clear. That works. And what I'm going to do is basically equivalent, but I think it's easier, is when I look at this, this looks like the denominator looks like a difference of 2 squares, and the numerator looks like one of the factors. So I'm going to think about 1 minus x as like 1 squared minus square root x squared. I'm going to kind of think about it that way. And this is really like the same thing as what Nate suggested. Certainly doing conjugates will work here. You'll get the exact same answer. I just think that this is kind of slick. Yes, sir. Absolutely. So I get 1/2. Everybody good there? Is 1/2 inside of negative root 2 to positive? I'm sorry, negative pi over 2 to positive pi over 2? Yeah, right? Pi over 2 is like 1.57. So we're in there. So this is just going to equal sine inverse of 1/2, which is unit circle. That's a unit circle value. 30 degrees or pi over 6. I know. And that's okay for right now. Like if you're just like, I am just rusty on this stuff, like this is something I can do. I just haven't looked at a unit circle in, like 12 weeks or whatever. Like, it's okay. It's okay. You'll have time to refresh, but you're seeing now that like, not as, like I knew this at one point, I just don't like know it in my bones. And that's okay. Again, I've been doing this for like 20 years. That's why it looks so easy. All right. Theorem 9 says if G is continuous and F is continuous, then their composition is continuous, which should be pretty straightforward here. Now, I left off some little details like G is continuous at A and F is continuous at G of A, but it's like, it's basically the same thing. So like if I look at h of x, I see that this looks like a composition of two functions, right? Where my outer function f is sine x, and my inner function, my g, is x squared. Can you guys see that? as a composition of two functions? Right? What's the domain for g of x? For x squared? All real numbers. Okay? What's the domain for f of x, for sine x? All real numbers. So what will be the domain for sine of x squared? All real numbers. So where is it continuous? All real numbers. Everybody's happy? Okay. Let's look at part B. The domain for the inner function is all real numbers. What's the domain for the outer function, though? 0 to infinity. Okay. So now we have to look at the range for 1 plus cosine x. What is the range for 1 plus cosine x? 0 to 2. That's excellent. Does everyone see how we got 0 to 2? What's the range for cosine? Negative 1 to 1. If we add 1, it's going to go from 0 to 2. Everybody's okay? Now, this is my range for this. This was my domain for this, was that. What's the problem, though? Yeah, I'm plugging 0 sometimes into the natural log, right? So whatever those x's are that make 1 plus cosine x equal to 0, those are not in the domain of the composition. What value of x is going to make cosine x equal to, what value of x is going to make 1 plus cosine x equal to 0? Give me 1. How about pi? Right? Cosine of pi is negative 1. 1 plus negative 1 is 0. But is that the only place where 1 plus cosine is going to equal 0? Yes, it's going to be pi and then everything coterminal to pi. Right? So this is continuous at all real numbers except pi and everything coterminal to it. Addie, you okay?
I'm Aaron.
I'm sorry, Aaron. Dang it. I'm working on names. I'm trying. Aaron. You're the Addie and you're the Aaron. Okay. My apologies. We're okay though?
Yeah.
I heard you two whispering. I want to make sure.
I just did not know how to write the coterminal
Okay.
other than writing everything else.
Yeah, so you just say, what this is saying here is pi, and then every 2 pi multiple of pi, right? So 2 pi times k, where k is an integer. So like 1 times 2 pi, or 2 times 2 pi, or negative 3 times 2 pi. All those things will, if you add it to pi, will give us another answer, right? Yes?
Why did you find the range of g of x for that at f of x?
Because, great question. So Violet asked, in part B, why did I care about the range of g of x, but I didn't in part A, right? So here's the reason. In part A, the outer function's domain was all real numbers. So it doesn't matter what g of x evaluates to. As long as it evaluates to something, I can plug that something into f. In part B, it matters what g of x outputs because I can't plug every single thing into f. The domain for f is restricted. So I had to then look, okay, what specific outputs from g are going to be a problem? And I had to trace those back to the inputs that give me that problematic output. Violet, did you understand any of what I just said?
Just a little bit.
Okay. Can I say it again?
Sure.
So the key is the outer function. So the outer function in part A was sine x. That domain is all real numbers. So it doesn't matter what g outputs. As long as it has an output, I can take f of it, right? And since the g for part A also has a domain of all real numbers, anything I put into g has an output. Any output from g I can plug into f, and that'll have an output. So everything works. Does that make sense?
Yeah.
Okay. In part B, the domain for f is restricted. It's just 0 to positive infinity. So not every output for g I'll be able to plug in necessarily, right? So let's look at g. Okay, any g I can plug anything in. That was continuous or had domain all real numbers. But the output for g gave me some things that I can't plug into f, right? Specifically in this case, it was 0. So I had to say, okay, where does g, or what values of x give me an output of 0 for g? We found one such as pi because we know we have infinitely many. And does that feel better?
Yeah.
Okay, I did a better job the second time through?
Probably.
Okay, we'll take it. I'll take it. So far, so good? We're still okay? Everybody else? Okay. The next piece is called the intermediate value theorem. This is one, along with the squeeze theorem, that we've seen so far that the AP will expect you to be able to quote by name and use in context. So the squeeze theorem has a name. The AP would expect you to quote the squeeze theorem by name, not write down what it is, but if you're using the squeeze theorem, you have to say you're using the squeeze theorem. And the same thing with the intermediate value theorem. Now, the intermediate value theorem definition here is technical, but the idea is really simple. So I'll read you the technical definition and I'll explain to you what it's saying. It says, suppose f is continuous on the closed interval from a to b. Let n be any number between f of a and f of b, assuming the two are not equal. Then we can conclude there exists some number c on the open interval from a to b such that f of c is equal to n. So if we look at the picture, the blue is our function f. So we have the interval from a to b. We're told f is continuous on that interval, so I can draw, there's points everywhere along, right? So I know that there's y coordinates then everywhere from f of a to f of b also. If I pick any value in between, say this n, I can find an x in between a and b that has that output. And I'm guaranteed to be able to do that because of continuity, right? If I didn't have the continuity, I would not have this guarantee because you'd have a gap in y coordinates or something. Could there be more than one x? Yes. Does this theorem at all help me find the x? No. It is just going to allow me to prove its existence. This is an existence theorem. It does not help you find anything. It just says that it has to be there. Okay, let's do an example. Example 10 says, show there's a root for the equation, yada, 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 between 1 and 2. So, first thing I want to do is I'm going to define an f of x to be this polynomial. I know this is continuous because it's a polynomial. Everybody okay? I need to state that because the condition for the intermediate value theorem requires continuity for the function. So I have to say that, and probably I should say everywhere. Let's be a little bit more specific. It's continuous everywhere. So far, so good. Now, I need to find a y-coordinate that's between 1 and 2, that's negative, and one that's positive, because I know 0 lies between. Everybody's okay with that? If I'm looking for a place where it has a 0, a solution, that's where the y-coordinate is 0. So if I find an x between or including 1 and 2 that's negative and a y that's positive, then I know somewhere in between there we had to cross the x-axis and we have a 0. That's what the intermediate value theorem is going to do. Where do you think I should check? Let's just check 1 and 2. If I do 1, that's 4 minus 6, that's negative 2, plus 3 is positive 1, minus 2 is negative 1. F of 2, that's 32, minus 24, that's 8, plus 6 more is 14, and then minus 2 is 12. Okay? Everybody's okay with that? So I'll say since f of 1 is less than 0, which is less than f of 2, the intermediate value theorem, I'm going to abbreviate that as IVT. That's a fine abbreviation for you to use. The AP will also recognize that abbreviation. States there exists, the symbol for there exists in mathematics is the backwards E. You can always write the words there exists. You don't have to do that. A C on the interval from 1 to 2 such that, I'm just doing ST as my abbreviation for such that f of C is equal to 0. And I'm done. So what I did, I showed the function was continuous. I found a y value above and below the y value that I need to find, right? So if I'm looking for y equals 0, I found a negative and a positive, and then I just stated the conditions for, or stated the intermediate value theorem. Have to show continuity first. Every time you run into an intermediate value theorem, it's the first thing you need to show. I'm saying this over and over and over again because in my experience, half of us forget to show continuity. Okay? Gotta remember continuity. It's often you just state this thing is continuous because it's this kind of function, and that's all you need to do. There's nothing to prove there. You just can state it, but you have to remember to say it. What do you guys think? Continuity. Okay. We have what? We have 20 minutes left. Here's what I want you to do, or here's what we're going to do. You'll probably need your tablet. You're going to open up your My AP. And we are going to do, oops, that's not what I wanted to do. I wanted to paste. You're going to use your group, and you're going to answer, there's 11 questions on the MyAP. Okay, everyone please do one. You guys can discuss in your group. You can agree on an answer. Okay? But we're going to do that. There are multiple choices. There's 11 of them, I think. So, go ahead. No big deal. So you guys can get up and move around so you're near your group. You can use a calculator. You can use your notes. That's all fine. The AP site grades it. And this will count as a homework quiz score, but it won't be like all right as a 10. I'll create some kind of tiers. Yes. That are fairly representative of the percentages for like 5, 4, 3, 2, 1 on an AP exam. So. Yes, it's the only quiz assigned to you in the MyAP.
There was like another thing.
Oh, I shouldn't have had anything else assigned.
It might have been a different.
Okay, might have been somebody else. Okay. So it looks like it took it. Next time when you do that, though, will you pick insert as printout rather than just as a file? So I don't have to open each one. It'll just be. So when you drag this in, it will probably. All right, let's do this. So if you drag this in, it'll give you like that option. You want to do printout rather than file. But otherwise, this is fine. Yeah, it's fine. Yep. Will you send me an email to remind me to make sure to go back and check it? Because this conversation, so much as I'd love to remember or think that I'll remember it, I'm not positive I will, and I don't want to forget. So you you log into your MyAP. Yes. Chapter 1, practice number 1 should be there staring you right away.
Oh. What if like x plus 1? So I think A and B are both correct.
So, like if you did f of, if you plug 1 in for x here, it'd be like f of 2, right?
Yeah.
So it just, you know what I mean? Like
1 in for x, so like.
So you'd be doing f of 2 instead of, when
yeah.
you did 1 in for x here, you just get f of 1.
And times g of x.
So it'd be g of 1, right?
Yeah. Alright, thank you.
My AP Classroom's like not working. I was doing this earlier too.
Oh, okay. Okay.
Because it's not like.
And it says you're in, but it just like everything's.
There's like an error. And I was doing that earlier because I was trying to.
Try that. Oh boy. This is error 400 even. Like. I think you have a trip to in your future.
Should I go now?
You can, what I would do is I would just look in off someone else, work together, write down like your responses that you want to do, and we'll just add them in later.
Okay.
Sound okay?
Yeah.
Okay. That feels the most simple and allows you to like contribute now and do the part that really matters.
The limit said zero, but it's just a point. So are we saying that it would be times one, or are we saying that it would be 0 times 1 because that changes our
I think it is.
How do you know what they're like trying to find?
That's what continuity that exists.
It's not going to the same.
Are you saying that they don't agree? They like let us see.
I was trying
Oh, they're just talking about the numbers that they got 0, negative, 3.
Oh yeah.
No.
Oh wait, no,
Zero.
yes, I realized. So you can't just plug it in. Does that
Well, but there's not an option that's like there is
Well, it says, oh, wait, oh, yeah. The Y value is usually more than the X value.
I think it's just 0 because it's equal. That doesn't. It's open circle. I think it needs an equal.
we know that A and B is
I think it's trying to show you. I think because A is not true. Like,
So it's X plus 1 is if there's a whole add says 0, but then there's an actual point and it's coming from
Oh, this is a limit.
you know what I'm saying?
Oh, wait, that goes out. 2.
So we know that as X plus 1
Yeah, you're right. There's one part where it would be like.
So what's the definition of multiple?
Yeah, it's just a whole.
When does a limit?
It goes to infinity and as it approaches.
Where the right hand side
I agree.
So then what's the
to confuse you.
nice.
But like f of 1 would be 2x, but the limit as x approaches 1.
Okay. That makes more sense. Thank you. So let's go.
Wait a second. So is A better?
You can use your calculator if you like.
No, it's a limit zero.
Is this on calc?
He said if it was
Well, they're gonna trace it.
They're
They're not gonna worry so much about it.
No, it is.
Oh,
You wanna try to get your money.
Yeah.
Does it make any difference in how hard
I guess
this
it's
is?
No, I'm.
Yeah, it's just like, yeah, like I'm not. Well, then, the site rate, and I'll be interested in how you guys do.
Yeah, I'm.
Yeah, it's like if it's like a 2 hour.
If we get that right, I'm sorry guys. Okay, now.
so now this one, should this be -203?
Yeah, I think that's right. Because even though there's a hole, it's still limit there.
Yeah.
Yeah.
Like traditionally, like 50% is like that.
So the limit would be at 2. So that sine of 2, I don't know what sine of 2 is. You can use it. Make sure your ratio is it should come out the same. 0.909. I mean, that is.
That's the answer.
Okay, I can try.
They give you. It's not C.
Wait, why did that?
Maybe it's B. It must be B.
It has to be his ex purchase too.
Oh wait, it could be.
It's gotta be it.
Yeah.
It wouldn't be the
I think it's.
You know what?
Absolutely.
No, they are right. No,
Yeah.
actually, no, you guys are right. It's E.
Yeah, it's not like we're just getting ready to 0. We're just like, we're going like this.
It might not exist.
I didn't look at it.
It's too big of a jump.
Right, the limit is the left hand and right hand going to the same spot. Where
I wasn't
it doesn't need to be defined here.
It was for a different reason.
No, the function is undefined. You're correct. The limit can exist even if it's, the function is undefined. So that's the distinction. So you're right, it is undefined, but the limit can still
You have to split it up because there's no limit as a
Right.
So I just, yes,
Count for the coefficients. Yeah, I think that's making sure you don't let your limit. Yeah, that's not, in general, they should be like, not monstrous. It's the first time you're doing it. It's still that.
okay, so when X is greater than 2.
As X, X is 2 from the left. So if you split the table down the middle, from the left is negative 1, from the right is 6.
I know the answer.
Okay, that should be right.
Oh, never mind.
Guys finish?
Whenever you approach, say two's here, try to go positive side.
I think if you press like Control plus, it'll make your screen. I'm gonna make it bigger if you're having trouble. So
Yeah, no, I just get kind of
okay. So I think really like here and in, I was like,
yeah, I just like
I know that like sometimes
From the left.
you know, like they write the questions and they put it in the format. It's
So I think it's two.
So, okay, so 2 times 3 now.
Yeah.
2 times 2
yes, because 2 plus is greater than 2. So you live there.
34? Wait, how do you
24 plus, 24 plus 8.
Oh wait, what's 34?
I got 32, but I don't know if that's right. I just like you know, when did we use right side? Oh wait, no.
Oh,
Be like A squared plus A squared.
Oh yeah.
I have plus there, yeah. We can do this.
H of X.
Do it.
I was just meter graph. 1 over. Yeah, remember that.
So what's the limit as the top?
I got 2 minutes. Sounds good, sounds good. Do you want to use your notebook?
No, it's fine. I just
How much does that make a minute?
And again, why did they give them to you? I'm glad you saw it.
I got 56.
You have 56? I low-key trust your answer with that.
Because, well, no, we'll use these numbers or these numbers. I think it's these numbers. I think it's these numbers.
Okay, sounds
And
good.
then you get like 24.
8 is 120.
This is
I feel like that should make just 59.
Because they're not going to. Oh, wait, I forgot. Okay. Okay. I think the H of X is 3
Oh, yeah, yeah. Sorry, I'm pretty sure number 1. And then we do the same thing. Well, like X squared, yeah. So like,
Quick before this thing. Oh my god.
Oh, wait, no, that's.
Okay.
Oh, that's.
Because then you can split this.
Is that the next class?
I think they missed the prayer. If you're, hold on a second, guys. If you're finished, you're fine. If you need to finish, you can finish at home. That's fine. If you want to stay here and work for a few minutes because you're like, I'm almost done, that's fine. I'm not going anywhere. Have a great weekend. Oh, you know what? Like, I probably have that screwed up then. It's fine then. Don't worry about it. Don't worry. Don't worry. If it did that, then that's my fault for the way I set it up. I might have had I probably set the due date for the end of the hour instead of in the future, which I should have. So it's fine.
Post your like lectures on there, right?
Yes.
You know how I can get those? I was just having trouble focusing.